here are the equations that we have to solve is reaction diffusion equation. I recall you that what I am looking at is a one-step model, reactive transforming product with heat release. One step, Arrhenius law. This is very particular. So just the thing I want to do will be in this model. In that case, if we want to understand the effect of the transverse diffusion process inside the wrinkle frame, what this diffusion process are going to produce. You are interested in that? First of all, let's simplify the problem the most you can. And this is simply to take out the change of density in order to avoid the hydrodynamical effect and look only to the diffusive effect. In that case, the only equation you have to solve is this one. Very simple equation. Let's say simple. Not so simple to solve. But you have the boundary condition, you have everything. So just to solve it. The only difference you have is that in the Laplacian now, you have a transverse component. That's the only difference with the previous analysis in the planar case. Okay, we are going to work in the frame attached, the reference frame attached to the reaction sheet. So the reaction sheet is its equation is here in reduced coordinate. This small a here is a reduced frame displacement, local, or depending on the transverse velocity, transverse component, or transverse okay, and the time. So if you are here, what you introduce to work in this problem is the displacement is relative to the flame position. You attach the referential frame to the moving front. Okay, so now your length here, your distance, this distance zeta here, is a measure of the distance to the flame sheet, local flame sheet. Okay? Yes. Now, so what you do is to change coordinate as usual, and now the equations are written here. These are the equations the same as before, written with this variable here. Okay, that's the only difference. And now, because you want to work, you want to apply the asymptotic analysis and the jumps that we obtain on the flame surface, so you have to follow the flame surface, otherwise you are lost. So here is the external equation. That is the equations that are verified in the preheat region, that is without reaction. This is the external equation. And you are working in an harmonic analysis. So you use the non-dimensional parameter here. So once again, the complex number, which is an unknown that you have to look at, is reduced by the transit time of a fluid particle across a flame, and the wavelength is kappa, is reduced by the thickness. So, excuse me, yes, it's reduced by the flame thickness. So now you work in Fourier analysis such a way that the perturbation of the mass fraction of the limiting component, you see what I do is, you know, I wrote first the flame displacement here, which is here, what is this term, in terms of this, where you introduce the Fourier transform of this amplitude, A, which is with a hat. This is a Fourier transform. And what I did now in the other field, that I look also to the same kind of structure for a Fourier analysis, but to avoid to have this, in the Fourier component, I define a tilde here, which is in fact multiplied by this displacement. This is just to simplify the presentation. So, because you are going, you know, because you are linear, you are going to simplify this alpha x at here, you know, so on both sides. So this is not necessary. To do that, you have to put it, or otherwise, yeah, but okay, it is not very important. So what the problem is to find out what is the reduced linear growth rate depending on the reduced wave number. Here are the equations, the same as before, written using the harmonic analysis. You see, you replace d over d2 by this strange, I don't know what it is. Is it zeta? I don't know. you replace every derivative, time derivative is replaced by this strange thing that you have here, and all the other are the same thing everywhere. That's all. Now, to solve such equation, you know, you see, sigma is an unknown. This growth rate is unknown. Kappa is known, and the flame speed is unknown. But no, the flame temperature, more precisely, the departure of the flame temperature from its value in the planar case, which is here called theta, F, this is also unknown. The variation of the flame temperature is also unknown. So you have two unknowns. Now, it's very clear to find that you have a particular solution of this problem, which is given by the gradient of the steady state. Why? You see, when you are in steady state, this is zero. This is zero. So you have this balanced by that, this balanced by that, okay? And now it's clear that the result is simply that this particular solution is a derivative with respect to space of the unsteady solution. This is a particular solution of the problem. Now, this problem is written outside the reaction sheet. Now, what you do is to solve, here are the boundary conditions that you are using, and now you have to find out a particular solution. And the particular solution that you are going to find, you look for in the form as before, as an exponential of the linear growth rate, the time dependence, or the Fourier transform of the time dependence. And now if you put this so this is a particular solution of the complete problem. This is the solution of the homogeneous problem, which is an exponential, which is solution of this quadratic equation. There are two roots that are here, such a way that this is a particular solution of the complete problem. This is the general solution to the homogeneous problem. And in order to make appearing the flame temperature, you put this and this minus that in such a way that at psi equals at zeta equals 0, which is the laminar, which is the reaction sheet, you have theta equals theta f. And this is the equation for theta. This is the equation for psi here. And now you look for a solution for psi in terms of S. And this psi now behind the flame, it is 0 because there is no limiting component. It's all burned. So you are looking for the solution in the preheated zone. Okay? And here, the solution that you obtain, the particular solution, the general solution, excuse me, that you have to find out is exponential this reduced variable with a coefficient here, which is similar to this obtained for the temperature, except that you have a Lewis number appearing here and appearing here. That's all. So, general solution. That's the solution. No, excuse me. So now you have the jump condition. You have to apply two jump conditions. One. And the asymptotic analysis you develop is this one, that you assume that the temperature, the departure of the temperature from the planar case multiplied by beta is of order unity. This is an unknown. Now you can apply immediately the second condition very easily. You apply that, and now you obtain this form. This, when you apply this condition, to this two problem, to this two solution. Okay, you obtain immediately the flame temperature in terms of the Lewis number. And now you understand why I am looking to a Lewis number close to unity in such a way that this term should be of order 1 over beta in such a way that the modification of the flame temperature is of order unity when beta goes to infinity. That is when the reaction sheet is going to 0, the thickness. This is for the flame temperature. Now, you use the first boundary condition, linear, first, and you linearize that, because we are linear. You linear that, you obtain this, and see if you put this equation obtained from the first, and this obtained for the second, put it together, you find defining the number small l like Lewis minus 1 times beta, you find this, what we call a dispersion relations, giving you the reduced growth rate in terms of the reduced wave number, okay? And what is the parameter that you have in this problem is only the beta, this parameter of order unity that you have here. That's all. So you have to solve this equation. That is an algebraic equation, so it's not a big problem now. Okay, and now you understand why we use this asymptotic limit of beta of Lewis minus 1 of order 1 over beta. Now, here again is what we call a dispersion relation. That is, was the solution give you the growth rate here in terms of the reduced wave number here. As you see now, the reduced wave number is appearing only to the square. See, this is the main difference with the hydrodynamic instability. The growth rate, only the square of the wave number is appearing in this problem. And this is because of the diffusion problem, all right? Because it is a reaction diffusion. Now, if you look first to the weakly covered limit, that say, okay, I am looking to wave number that are smaller than the inverse of the flame thickness. That means that wavelengths are large compared to the flame thickness, okay? I look to that. So I look to the solution for this. Kappa square is small, and so the rate is also small. And here is the relation that you have in this limit for the growth rate in terms of reduced growth rate in terms of reduced wave number. And now, and this is written again in original variable here. Okay, this is a reduced variable. This is a diffusion equation that I have discussed, that I have anticipated to begin with in the last lecture. But now, turns out that the diffusion coefficient you have here could change sign. What does that mean? If the diffusion coefficient of the diffusion equation is negative, you have a strongly unstable system. Strongly unstable. The relaxation of the diffusion equation is valid only when the diffusion coefficient is positive. And this is something very troubling. Very surprising. Because it turns out that only diffusion process could destabilize a problem. And this is a very, very deep physical insight into what Turing, this famous, Turing, this famous English, was studying to understand morphogenesis. What does that mean? That means the following. Only diffusion and reaction can create structure, starting from something which is equilibrium uniform. This instability, diffusional instability, can create structure. Why? Because the linear growth rate is for any perturbation is non-zero. So, starting from something uniform, you can go to a structure. And this why Turing tried to understand, in a sense, what is called the morphogenesis, how the structure can be built from something uniform. This is related to the life, to how the life starts. But we are far from that. But this is the first idea. The first idea is the following: is that you can create a structure just because of the difference of diffusion coefficient. And this is just the opposite of what I said to begin with. I told you that the diffusion process is all the time relaxing. Yes, be careful when you have competitive effect in diffusion. And this is was doing first Turing to understand with morphogenesis, putting a mixture of with reaction and so on with two diffusion coefficient competitive, that starting from uniform, you create non-uniform things. You are create structure, spatial and temporal structure. And it is true that, as I say, that if this term is positive, there is no problem. This, once again, you are stabilizing diffusion frame. The diffusion equation is all the time stabilizing, provided the diffusion coefficient is positive. Because of the competition of two diffusion processes, you could end up with a negative diffusion coefficient. This is what tell you, okay, so now if you put, what you can do is to look to the same, here was the first expansion is small kappa. Now you can look to the next order in power of kappa. And then the next order, which is kappa to the fourth, this is always stabilizing. So now, if you are stabilized, this term is negative. So you are, so if this term is negative, you are stabilizing all the wavelengths, which means that you are intrinsically stable against any fluctuations of the surface. But if you are unstable, the short wavelengths are all the time stabilized. You just have to go to this equation here and look to the next order development in kappa square. Kappa square, the follow, because you have only kappa square here. And now the next order is kappa square square. So it is kappa to the fourth. And this gives you all the time, you have a minus sign here, telling you that the next order is stabilizing. This tells you that you should have this kind of picture thinking about the linear growth rate in terms of the wave number. You are all the time stabilizing the very small wave number, contrary to what Landau say. And this is also working when you consider the coupling of the hydrodynamic instability that I have described and the diffusion instability. Yes. And let me tell you also for the history that Zeldovich understands that for flames. But he did not clearly see the impact that this can have on the general physics. You know, and Turing was the one. Turing was a famous mathematician. Huh? And he picks up the general conclusion that one can have from this instability by competition of diffusion. Okay. This is a summarize of the result. The limiting species is called F. The species in excess. No, you have okay. If you have a lean mixture of hydrocarbon, the limiting species is larger. It has a large dimension than the species. So because now if you have a lean mixture, the excess species is the oxidant, and the oxidant is much smaller than the species. That's a molecule of oxygen is much smaller than molecule of, let's say, acetylene or what you like, except for methane. For methane, one has to be careful. But so in a sense, every time the lean mixture of heavy hydrocarbon is thermodiffusively stable. However, the rich mixture of heavy hydrocarbon could be unstable thermodynamically. And vice versa, when you look for a light limiting species like hydrogen, you have to be careful, it is just the opposite. Now, few words when you put together the two results that I have just mentioned. This dashed line here is a Landau, Dario-Landau analysis. The growth rate is linear in terms of the wave number. This is the case where you are diffusively stable, so you stabilize the short wavelengths, large K, but you stabilize also the short wavelength when you are thermodynamically unstable, but the range of unstable wavelengths is much larger than the range of unstable number. And this is clearly observed in experiments. For example, a propane lean flame should be diffusively stable, but as all the flame, unstable by the hydrodynamics. So the cells are very large. Now, if you take a rich propane flame, now the diffusion is destabilizing, so you have a lot of smaller structure that appear on the flame. And this is, you see that you superimposing this large cellular structure coming from hydrodynamics to the small structures that you have. You see a lot of small structures that are coming from the diffusion flame. So this is, let's say, a result, an important result for flame dynamics. It's not new. The problem was finished, let's say, 40 years ago, more than 40 years ago. A decisive step was also developed by Szywaczyński, who tried to develop a nonlinear analysis to see what will be the effects of the nonlinear term. It turns out that the effects that appear through a geometrical term which is associated with the Huygens construction, explaining these cusps that you have everywhere. And this was, in fact, Grisha Szywaczyński did that when he was a student of Zeldovich, by the way. And he was Jewish, and he has to immigrate from Russia, and he came in Europe around 78, something like that, 77, 78. And all the calculation he did in Russia, he keeps that as a treasure to be recognized in Western country when he arrived. And he was recognized immediately. And now he is a famous theoretical combustion scientist. He is now living part in Israel and part in UK. There are another phenomena that I am not going to discuss, is that when the Lewis number is larger, now beta Lewis minus 1 now become of order 10. You see something like that. Now you have another instability that appear, and I would not to discuss it except the people that are looking to solid combustion, because this appear, such large Lewis number appears in solid combustion. And in that case, you have an imaginary part, in contrast to what I said before, the growth rate was all the time real. Here, it becomes imaginary and corresponding to oscillation. So that's what we call a an oscillatory instability. So this is to finish. We have 10 minutes. Now we are going to change completely of topic. You are going to go to detonation. That's, and I want to. So it's. And I will be back to. I do not have the paper here, so it should be 9. Should be 9. Where is it? I guess it is this one. No, this is turbulent flame, so it is 10. So I will start that just. Oh my goodness. So I am going now to just to start with supersonic waves. Wait a minute. I skipped the flame quenching problem. Okay, I will be back. I see there is another problem that I would like to present to you is the flame quenching by heat losses of flame. But I can do that afterwards, after the turbulent. This is just the air conditioning? Okay. So we change completely of topic. We will be back because we are going to make connection between the two. And I will start with some background, considering model of hyperbolic equation for the formation of discontinuity. So this is a mathematical problem which was developed in the 19th century by Riemann, by the famous scientific called Riemann. So let's start to present what is a planar shock wave. You start with the experiment the following. You have a tube full of gas and by a wall, and assume that this wall is a piston. And now make moving the piston. The wall is, no matter can cross the wall. So as soon as the wall is put in motion, all the gas close to the wall follow with the same velocity. But far ahead, the velocity is at rest. So the question is, you cannot say that all the column of the gas is instant. If the column is infinite, is immediately set in motion by starting a motion of the piston. You should propagate the difference of density of velocity, and this is due to compressible waves that propagate upstream. But after a while, these compressible waves degenerate in a discontinuity where in front of it the gas is at rest, and behind it the gas is uniform with the velocity of the piston. And this discontinuity, you know, when I sit on the discontinuity, I see the gas propagating entering the discontinuity with the propagation velocity d, and getting out with the velocity ue. It turns out that this is a shock wave, and that one of the problem, very difficult problem, that people doing numerics know very well, and have to cure this, that the thickness of this shock wave is microscopic. It has a few mean free paths, which means what? That you cannot study the inner structure of a detonation, of a shock that you have here, working with the with a hydrodynamical equation, because the hydrodynamical equation, macroscopic equation, assume that all the lengths are much larger than the okay. This is true except when the Mach number is close to unity, when the Mach number of the flow. So I forgot to tell you that the velocity of this discontinuity called shock is necessarily larger than the laminar, than the sound speed, necessarily. So now, if you have a weak shock with a propagation velocity just above the sound speed, Mach equal 1.1 or 1.05. In that case, the thickness becomes larger, as I will try to explain you. And in that case, you can be back with a macroscopic equation to understand the detonation, the shock structure, because now you have enough mean free path to use thickness to use a macroscopic equation. One of wonderful work, mathematical work, pure mathematical work, was a work developed by Riemann in the middle of the 19th century. He was very young, almost less than 30 years. He was very young, and he was a fantastic mathematician. He was a student of Gauss, the one I told you that describes the geometry of the surface. He was a student of Gauss. It turns out that this shock wave can be seen as a discontinuity in the solution of the Euler equation. So, because it is very thin, and so on. And now the question was developed by Riemann was the following. Okay, I know the acoustics. Acoustic is a linearization of the Euler equation, and there is no point. It is acoustics, is, I will be back to that, but just I will finish. Acoustics is a solution of the Euler equation when you assume that there is no dissipation. You assume that there is no dissipation, so you assume that the pressure and the density are related by the isentropic relation. And when you do that, you close the system, and you develop acoustic waves. And the problem of Riemann was of Riemann was, okay, what is going to appear if I get out from it is a linear analysis acoustic. I want to see what is going to, what the nonlinear terms are going to produce. It turns out that these small nonlinear terms are going to produce a catastrophe, which means that the solution is diverging in finite time. And this is a work of Riemann, and I am going to start with this tomorrow. Okay, thank you very much for today.